Okay, so chapter 1 is an introduction to statistics. So, in this course, we're going to talk about the math and statistics behind behavioral sciences. So, it'll be very important that we build each week on the skills you need to know to be successful in the course. So, in terms of behavioral sciences, a statistic is a type of procedure that's performed to lead to a certain outcome. We use statistics to organize and summarize information and to determine what general conclusions and justifications we can make about results that we've obtained, usually results involving research. The goal of a statistical procedure is to find accurate and meaningful interpretations, and to have a standardized evaluation procedure for others to use in the future. In order to understand how statistics work, we have to know about a population and a sample. So, a population will be the set of individuals of interest that we're studying in a particular research study. And the population will vary by size. Usually, having a large population tends to yield better results. And a sample is going to be the set of individuals that are selected to participate in a research study from a particular population. That's usually intended to represent the population that's present in a research study. For example, if we wanted to research the level of satisfaction of students at Tarrant County colleges, our population would be all of the students who attend any campus of Tarrant County College. And we could take a sample to participate in our research study by randomly selecting participants from the population, students from Tarrant County, to participate in the research study. So if I included students who attend Dallas County colleges, then they aren't representative of my population I'm trying to study, so they should not be included. I hope that makes sense. Here's a little chart that can also help you understand the relationship between a population and a sample. That population is going to be all the individuals that we're trying to study. The sample is selected from the population, and the sample is going to include the individuals selected to participate in the research study. And the results from the sample, we then can generalize to the population because we always want to have a good representative sample. So if I've randomly chosen people from my population, even if somebody didn't participate, I should be able to generalize those results because everyone in my population should in some way be equal or similar because they're all students at Tarrant County colleges. Some other terms that you have to be familiar with is a variable, which is a thing, a characteristic or a condition that can change, or it can have different values for different individuals. So I always tell students that a variable is just a thing. It's a thing that can be different for every person. Data, sorry about that, had my alarm going. Data, meaning more than one thing, is a measurement or observation of a variable. So I collect data, I collect information about whatever thing I'm studying. A data set is going to be the collection of all my measurements and observations I'm making about my things, my variables. And a datum, which is singular, is going to be a single measurement or observation. It's typically a score or a raw score in statistics. Some other terms you need to know is a parameter and a statistic. A parameter is going to be a value, usually a numerical value, that describes the population. So remember, the population is everybody I'm trying to study. So we're going to have parameters or values for that population, and it's going to be derived from the measurements of the individuals in the population. So I'm going to get my parameters based on the numbers from my population. A statistic is going to be a value or a numerical value that represents my sample. Remember, my sample comes from my population, and that statistic is going to be derived from measuring only the individuals who are part of my sample. Some other terms we need to know are the difference between descriptive and inferential statistics. A descriptive statistic is going to be a statistic that describes or summarizes and organizes and simplifies data. So, typical types of descriptive statistics are going to be things like tables and graphs and averages that describe the statistics, whereas inferential statistics are going to be those study samples that make generalizations about the population from where they were selected. So when we have inferential statistics, we are able to interpret that experimental data. Commonly, inferential statistics might be referred to as sampling errors, or we may say something has statistical significance, which we generally want if we're doing research. So we want to be able to describe those inferential statistics. So remember, a sample is never identical to the population. They're not the same. The population should have way more people, and the sample should be randomly selected from the population. But when we have that with our inferential statistics, sometimes we can have sampling errors. And a sampling error is a discrepancy that exists between a sample statistic and the corresponding population parameter. Because we can't say that they're exactly alike. We can make generalizations about the population, but we can't say both groups are equal. For example, whenever there's a vote or there's a poll about something, there's always a margin of error. So if you hear that this poll was taken from a sample of registered voters and has a margin of error plus or minus 4 percentage points, that's letting you know that it was just a sample of the population. It's not truly representative of how everyone feels. And that's how sometimes you can get election results that are quite different than what actually happens. So let's do a learning check. So throughout each of our chapters, I'm going to give you questions, and I want you to try to see if you can figure out the correct answer based on the lecture and things we've discussed as a sort of check on your knowledge. So here's our first learning check. A researcher is interested in the effect of the amount of sleep on high school students' exam scores, and a group of 75 high school boys agreed to participate in the study. So the boys are A, a statistic, B, a variable, C, a parameter, or D, a sample. So I'm going to give you a few moments to think about the correct answer. And hopefully everyone's thought of the answer. The correct answer would be D, a sample. So those 75 boys who've agreed to participate were hopefully taken from a larger group, a larger population. Here is a second learning check. I want you to decide if each of the following statements are true or false. The first statement is most research studies data uses data from samples. True or false? Or when a sample differs from the population, there is a systematic difference between groups. True or false? Give you a few minutes to think about both of those. So for the first one, it is true. A sample is used because it's not feasible or possible to measure every single person in a population. So most research does study data from a sample. And for the second example, it is false. A sampling error due to random influence may produce unsystematic group difference. Okay, let's move on to the next set of vocabulary terms, and that is observations, measurements, and variables. So first off, when we think of science and psychology, we have to realize that it's empirical. It's based on observation. The scores that make up the data from a research study are obtained by observing and measuring variables. The process of measurement is going to consist of applying carefully defined measurement procedures for each variable. When we have those research studies, we can also have constructs and operational definitions that must be taken into account. A construct is going to be an internal attribute or characteristic that we can't directly observe. It's useful for describing and explaining behavior, but it's not something we can directly see. An operational definition is going to identify a set of operations for measuring an observable behavior. And it's going to use those results of measurement to provide a definition and a measurement of a hypothetical construct. For example, if I am trying to research whether or not children develop proper academic gains in K-12 education, I would need to operationally define what it means to be a child, because somebody else who uses my research in the future may have different parameters and choose the wrong population for what it means to be a child. Because if I only research children from age 5 to 16, and somebody else views a child as someone who's from birth to 18, I could get very different results. So we always have to have good operational definitions that help us identify what set of operations we're measuring. What behaviors are we looking for? And what does that look like if somebody else wants to do that? We also need to know the difference between a discrete and a continuous variable. A discrete variable is going to have separate, indivisible categories. There's no values that exist between those two neighboring categories, whereas a continuous variable has an infinite number of possible values between any two observed values. It's divisible into an infinite number of fractional parts. Real limits of the continuous variables are going to be the boundaries of intervals for scores that are represented on a continuous number line. The real limit could be separating two adjacent scores, and they could be located exactly halfway between the two scores. Each score can have two real limits. The upper real limit can mark the very top of an interval of scores, and the lower real limit can mark the very bottom of an interval of scores. So the main thing you want to remember is that when we have real limits, that means we have boundaries for intervals of scores. So 10 to 20, 20 to 30, 30 to 40 on a continuous number line. We also can have different scales of measurement. Measurement will assign individuals or events to categories. Those categories can be names such as introvert, or extrovert, employed or unemployed, happy or sad. They can also be numerical values such as 68 inches or 175 pounds. Those categories are used to measure a variable that makes up a scale of measurement. There can be relationships between the categories that help us determine the different types of scales we'll use. And you might remember from your math class that when it comes to scales of measurement, we have nominal, ordinal, interval, and ratio scales. Those nominal scales are going to be those labels like gender, diagnoses, experimental or control group. Those ordinal scales are going to be categories of observations like rank or size. Intervals will have to do with ordered categories or specific intervals of categories like temperature, IQ, like a golf score. And then ratios have to do with equal intervals between categories and with an absolute 0 point. Like what are the number of correct answers given? What was the time used to complete a task? How much did the person gain in height or weight since last year? Okay, so it's time for another learning check. So if we're doing a study and we're trying to assess the optimal number or the optimal size, the number of members of a study group, so we're trying to assess the optimal size for a study group, the variable size of the group would be A, discrete and interval, B, continuous and ordinal, C, discrete and ratio, or D, continuous and interval. So take a few moments to think about what the correct answer might be. And here is that correct answer. It's going to be C. So it's going to be something that's discrete and ratio. Here's another learning check for true or false. The first statement says variables that cannot be measured directly cannot be studied scientifically, and research measurements are made using specific procedures that define constructs. Take a few moments to think true or false for each. And here are those correct answers. For the first one, we have false because constructs or interval states can only be observed indirectly. They can't be operationally measured. And the second one is true because our operational definitions are going to help us assure consistent measurement and provide construct definitions. Now let's discuss 3 data structures, research methods, and statistics. So a data structure is something like descriptive research where we look at individual variables. We can have one or more variables that are measured per person. A statistic will describe that observed variable. We can use category or numerical variables, and we're not really concerned about the relationship that exists between variables when we're just trying to describe the research. When we look at relationships between variables, we can have 2 or more variables that are observed and measured in order to determine a relationship. The resulting measurement can be classified into 2 distinct data structures that are usually used to determine what type of relationship exists. Is it a causal relationship or not? And then for the correlational method, we might have one group of participants where we measure 2 variables for each participant, and the goal will be to describe the type and magnitude of the relationship that exists. And there can be patterns that help us reveal relationships, but this is a non-experimental method of study. Here's an example of the correlational method where we have one group with 2 variables that are measured for each individual. So we can look at face time an academic performance, and we can see for all of those students their number of, when it comes to how much face time they have for their academic experiences, and then their associated academic performance. When it comes to limitations of the correlational method, we know that we can demonstrate the existence of a relationship between two variables, but we cannot provide an explanation for the relationship. We can't say why it's happened. And the biggest thing we always want to remember with correlational research is that it does not show us a cause and effect relationship. Correlation does not equal causation. For example, if we go back to this example, we can see that, is there a relationship between having um, Facebook time and having increased Facebook time and a person's level of academic performance? Perhaps there is a relationship between those two things. When we look at relationships between variables, we also have to think about experimental and non-experimental methods. When we use these types of methods, we compare two or more groups of scores. We can have one variable that defines the group. Our scores are measured on the second variable, and both experimental and non-experimental studies can use this structure. For example, if we're looking at experimental and non-experimental methods, we could look at the variable of type of video game, which could describe both groups who are viewing violent and non-violent video games. And then we can also look at a second variable, aggressive behavior. And we can use that to obtain scores as well. Like, is the violent group demonstrating aggressive behavior? Is the group that's using a lot of nonviolent, seeing a lot of nonviolent video games, are they engaging in aggressive behavior? So when it comes to the experimental method, the whole goal of the experimental method is to demonstrate a cause and effect relationship between two variables. We usually manipulate things with an experimental method. We'll have one variable that's determined by the experimental that is manipulated. And we always want to have controls that help us rule out influences of other variables, which we call extraneous variables. And these extraneous variables are things we can't control in a research study. So these could be participant variables or things that exist in the environment. So when it comes to experimental research, we can have an independent variable and a dependent variable. An independent variable is going to be the variable that is manipulated by the researcher. It's called an independent variable because no other variable in the study influences its value. It's actually manipulated prior to observing the dependent variable. And the dependent variable is the one that is being observed to see whether or not it is having an effect on treatment. It's called a dependent variable because its value is thought to depend on the independent variable. So when we are trying to have experimental research, we also have to try to control our research study. So some of the ways we can control the research study is to have random assignment, to match subjects as much as possible, and to hold the level of some potentially influential variables constant. So if I'm going to randomly assign subjects, that means I'm going to take individuals from my sample and I'm going to put them in group A or group B, and I'm going to do it randomly. And I'm going to try to match, or I can try to match those subjects as much as possible. Or I can have some type of variable that I make sure is constant for both groups, such as noise. Both groups are exposed to it. And then we also have control conditions where individuals are in the control group, they don't receive the experimental treatment. So oftentimes the experimental treatment is the drug, and my control group won't get it. They're either going to get no treatment or they will receive a placebo, which is like a sugar pill or some type of neutral stimulus that has no effect. And the whole purpose of a control group is to provide a comparison group for the experimental group. So I can say I gave my experimental group something that worked, whereas I didn't give my control group anything, and it didn't help them. They didn't get better. An experimental condition occurs when the individuals who receive the experimental treatment are exposed to the experimental condition. For our non-experimental methods, we can have non-equivalent groups where the researcher compares groups of scores. The researcher cannot control who goes into either of those groups either. We might also have a pre-test or a post-test where an individual is measured at 2 points in time. The researcher can't control the influence of the passage of time from the pre-test and the post-test. And that experimental variable is considered quasi-independent. Here in this figure 1.7 are some examples of non-experimental study. We can see that we have one variable where participant location is the quasi-independent variable, suburban versus rural. It's considered quasi-independent because we can't control it. It's there. You're either in a suburban area or a rural area. It's not manipulated, but it's used to create those two groups. And then my second variable might be verbal test scores, which is my dependent variable. So I'm measuring verbal test scores in each group, but I really can't control where they are. And then here's an example of other non-experimental studies. We could look at time and depression scores. So it's considered quasi-independent because the amount of time before therapy or after therapy can't be manipulated. It just is. But they can help create our two groups. And then depression scores are going to be my dependent variable. It's going to be what's measured between both of my groups to see if there's a difference. Okay, it's time for our third learning check. Here's our question. Researchers observed the students' exam scores. Researchers observed that student exam scores were higher the more sleep they had the night before. This study is descriptive, experimental comparison of groups, a non-experimental comparison of groups, or correlational. Take a few moments and think of your answer. And the correct answer is correlational because researchers are assuming that there's a correlation between exam scores and the amount of sleep that a person received the night before. There's that relationship that exists between those two variables. Here are our true-false questions for our third learning check. First question, all research methods have an independent variable. Second question or statement, all research methods can show cause and effect relationships. Take a few moments to think about these two choices. For our first one, the answer is false. Correlational methods do not need an independent variable. And the second one is also false because only experiments have controls that influence participants and environmental variables. For statistical notation, statistics uses operations and notations that you've already learned. And in Appendix A of your textbook, there's a mathematical review of statistical notations. Those statistical notations use scores that often are referred to as X and Y. Uppercase N is the number of scores in the population, whereas lowercase n is the number of scores in a sample. Summation notation occurs when many statistical procedures involve summing or adding up a set of scores. The summation sign is kind of that backwards E that stands for summation, and it's always followed by a symbol or an equation that defines what is to be summed. The summation is done after operations are first performed, so operations in parentheses, squaring, multiplication, and division. have to be done first, and then summation happens. And summation is done before other addition or subtraction. So you want to do what's in parentheses, or squaring or multiplication and division first, and then that addition and subtraction after. So here's our fourth learning check. If we had summation x squared plus 47, it is instructing you to do what? A, square each score and adds 47 to it, then sum those numbers. B, square each score, add up the squared scores, then add 47 to that sum. C, add 47 to each score, square the result, and sum those numbers. Or D, add up the scores, square that sum, and add 47 to it. I'm going to give you a few minutes to think of your answer choice. The correct answer is going to be B. So first you want to square each score and then add 47, because you want to do what's in parentheses, what's squared, multiplication or division first, and then add or subtract. And then for our true false, decide if each of the following equations is true or false. Summation of x squared equals parentheses summation of x also squared, or for the second one, parentheses summation of x times parentheses summation x equals summation x squared. Give you a few moments to think of your choices. And for our first one, it is false. When the operations are performed in a different order, the results will be different. And for the second one, that is true. The definition of sum x squared is indeed sum x times sum x. Okay, so that is everything that I hope will help you have a better understanding of the information in Chapter 1.